Water, flowing relentlessly for millions of years, carving through stone, sustaining life across vast landscapes. This is the story of the Colorado River, the lifeblood of the American West. But today, this mighty river is in crisis.
As key agreements governing the Colorado River approach expiration, the urgency to renegotiate these terms is escalating.
These ghostly white rings at Lake Mead tell a story of decline, marking where water once reached before receding to historic lows.
Experts warn that ongoing drought, increased temperatures, and reduced snowpack in the Rockies complicate these negotiations.
The contrast couldn't be more stark. Desert cities thrive while the river that sustains them slowly diminishes. 40 million people and economies worth $1.4 trillion hang in the balance as this lifeline of the Southwest faces unprecedented challenges. But there's more to this story than what meets the eye. Beyond the visible crisis lies a complex web of geological and hydrological systems, some formed over millions of years, that may hold both secrets and solutions to the Colorado River's fate. What hidden forces are shaping the future of America's most contested river, and what can they tell us about our path forward? The Colorado River begins as snowmelt in the Rocky Mountains, carving a 1,150-mile path through 7 U.S. states before crossing into Mexico and historically emptying into the Gulf of California. For thousands of years, indigenous peoples thrived along its banks. Then came European settlers, massive irrigation projects, and some of the world's most impressive dams, transforming a wild river into a managed lifeline for the American Southwest. Today, the Colorado supports massive agricultural operations, major metropolitan areas like Las Vegas, Phoenix, and Los Angeles, critical energy production, and countless ecosystems. It's one of the most heavily used and regulated rivers on the planet. But beneath this visible story of human engineering and dependence lies another tale, one of complex geological systems, hidden water pathways, and ancient processes now being disrupted in ways we're only beginning to understand. The surface crisis is impossible to ignore. The Colorado River Basin is experiencing its worst drought in at least 100 to 200 years, a mega-drought that has persisted for over 2 decades. The evidence is stark. Lake Mead, America's largest reservoir, now sits at approximately 30% of capacity. Lake Powell fares little better. Together, they represent a massive water deficit that continues to grow year after year. These declining water levels threaten more than just water supply. At Hoover Dam, if Lake Mead drops another 125 feet, water will no longer flow through the turbines, cutting off a power source that serves 1.3 million people. In California's Imperial Valley, farmers who rely on Colorado River water to grow about 80% of the nation's winter vegetables face increasing restrictions and difficult choices about which fields to fallow. Cities across the Southwest have implemented increasingly strict water restrictions. Las Vegas has paid residents to remove grass lawns. Phoenix limits outdoor watering, and Los Angeles has invested billions in water recycling and conservation. But these visible challenges stem from a fundamental problem. When the Colorado River Compact was signed in 1922, it allocated 17.5 million acre-feet of water annually. Yet today, the river consistently delivers only 12 to 13 million acre-feet, creating a mathematical impossibility that no amount of conservation can fully resolve. To truly understand the Colorado River crisis, we need to look deeper, much deeper, into the geological story that began long before humans arrived. The Grand Canyon offers a perfect cross-section of this history with rock layers that span nearly 2 billion years. Contrary to what many believe, the Colorado River didn't simply erode the Grand Canyon over time. Rather, as the Colorado Plateau gradually uplifted, the river maintained its course, cutting downward as the land rose around it. a process geologists call antecedence. This geological history created a complex underground structure. Some rock layers, like sandstone, allow water to flow through easily. Others, like shale, act as barriers. The result is a subterranean network of aquifers and confining layers that few people ever see, yet profoundly impact water availability. This hidden connection between groundwater and surface water becomes visible in dramatic ways. Parts of Arizona are literally sinking as groundwater is pumped faster than it can naturally recharge, creating fissures and sinkholes that damage infrastructure and permanently reduce aquifer capacity. Recent research has revealed how fault lines and fractures serve as highways for water movement between the surface and deep underground. These pathways mean that pumping groundwater in one location can reduce river flows miles away, often with a time delay that makes cause and effect difficult to trace. Using advanced imaging technologies like ground-penetrating radar and electromagnetic surveys, scientists are only now mapping these hidden connections, revealing a far more interconnected system than previously understood. The Colorado River's water doesn't just flow on the surface, it exists in a continuous cycle, from rain and snow to surface water to groundwater and back again. Understanding this complete system is essential to addressing the crisis. When snow melts in the Rocky Mountains, not all of it flows directly into streams and rivers. A significant portion infiltrates through soil and rock, entering vast underground aquifer systems that may hold water for decades or even centuries before releasing it back to the surface. These aquifers come in different forms. Unconfined aquifers interact relatively quickly with surface water, but confined aquifers, trapped between impermeable layers, can create pressurized systems that drive natural springs and maintain river flows during drought. In 2023, researchers announced the discovery of paleo valleys beneath the modern Colorado River, ancient river channels now filled with sediment but containing massive amounts of water. These hidden reserves could be crucial for future management, but they're also vulnerable to depletion. When we pump groundwater near rivers like the Colorado, we're not just taking from a separate system. Studies show that up to 50% of groundwater pumped from wells near rivers is water that would have eventually made its way to the river, effectively reducing river flow in ways that may not become apparent for years. The connection between groundwater and surface water in the Colorado Basin is one of the most critical and least understood aspects of the current crisis. Every gallon we pump from underground can mean less water in the river downstream. It's just a matter of when, not if. Climate change acts as an invisible accelerant to the Colorado River crisis. Since 1970, average temperatures in the basin have increased by 1.6 degrees Celsius, with some areas warming by over 3 degrees Celsius, fundamentally altering the region's hydrology. One surprising factor is dust. As increased drought leads to more bare soil across the southwest, wind deposits this dust on mountain snowpack. Dark dust particles absorb more sunlight than pristine white snow, accelerating melt by up to 6 weeks earlier. The data is clear. Snowpack that feeds the Colorado has declined by more than 20% since the 1950s. And it's not just less snow, it's earlier melt, which means less water when it's needed most during summer months. Scientists now warn that what we're experiencing isn't just drought, a temporary condition, but aridification, a permanent transition to a drier climate. This distinction matters profoundly for how we plan for the future. Even the most optimistic climate projections suggest Colorado river flows will decrease by at least 9% by mid-century, with some models predicting declines of up to 31%. These aren't just numbers. They represent an existential challenge for the Southwest. Higher temperatures don't just affect snowmelt. They increase evaporation from reservoirs like Lake Mead, which loses over 6 feet of water annually to evaporation, and from soil, reducing the amount of precipitation that actually makes it into the river system. The Colorado River once teemed with unique fish species found nowhere else on Earth. Today, 4 of these native fish are endangered, clinging to existence in fragmented habitats. They're living indicators of the river's health, or lack thereof. Since 1996, scientists have conducted periodic high-flow experiments, controlled floods released from dams to restore sandbars and natural river dynamics. These engineered flows attempt to mimic the river's natural rhythms that shaped ecosystems for millennia. Our people have lived alongside this river for countless generations. We've always understood it as a living being with its own needs and cycles. This modern crisis was foretold in our stories about what happens when that relationship falls out of balance. Riparian zones, the green ribbons of life along the river's edges, support over 70% of the region's wildlife species while comprising less than 1% of the landscape. As water levels drop, these crucial habitats disappear, though restoration efforts show promise in some areas. Even the tiniest life forms play crucial roles. The Colorado's sediments host complex microbial communities that filter pollutants, cycle nutrients, and support the entire food web. As river dynamics change, these microscopic ecosystems face disruption that reverberates throughout the system. The connection between surface water and groundwater becomes most visible through plants. Cottonwoods and willows along the river send roots deep to access groundwater. When that water table drops due to pumping or reduced river flows, these sentinel species are often the first to show signs of stress. The foundation of Colorado River management, the 1922 Colorado River Compact, was negotiated during one of the wettest periods in the river's history. This created an overly optimistic view of available water that haunts management efforts to this day. Today, the 7 basin states find themselves in increasingly tense negotiations. Upper basin states, Wyoming, Colorado, Utah, New Mexico, argue they haven't yet used their full allocation, while lower basin states, Nevada, Arizona, California, face immediate shortages that threaten existing uses. Often overlooked in these discussions are the 30 Native American tribes in the basin. Despite having rights to approximately 25% of the river's water, often with senior priority dates, many tribes lack the infrastructure to fully use their allocations due to historical inequities in funding and development. Innovation offers some hope. Las Vegas now recycles 99% of indoor water use. Farmers are adopting precision irrigation technologies that reduce water use by up to 40%. And research into more efficient desalination could provide new supplies for coastal areas, reducing pressure on the Colorado. Water banking, intentionally storing unused water in underground aquifers, represents one promising approach. Unlike surface reservoirs that lose water to evaporation, these underground reserves can store water for decades with minimal loss. The urban-rural divide remains a significant challenge. While cities use only about 12% of the Colorado's water, they represent most of the population and economic activity. Agriculture uses roughly 80% of the water while producing much less economic output, yet feeds millions of people and remains culturally significant. The Colorado River crisis reveals itself in visible ways: receding reservoirs, parched landscapes, and struggling communities. But as we've seen, the full story runs much deeper, through ancient rock layers, hidden aquifers, and complex ecological connections. We need a fundamental rethinking of water rights in the West. The solution will require both cutting-edge technology and traditional knowledge. We're past the point where any single approach will work. We need a portfolio of solutions. Despite the challenges, success stories exist throughout the basin. Watersheds are being restored through collaborative efforts. Cities have reduced per capita water use dramatically, and farmers are growing more food with less water through innovation and adaptation. Las Vegas has reduced its water consumption by 47% since 2002, despite adding 750,000 residents. Similar efforts across the basin prove that prosperity doesn't require wasteful water use, an essential perspective as we face a drier future. There are many ways to learn more and get involved. Support water conservation initiatives in your community. Research your local water sources and challenges. Contact elected officials about sustainable water policy. And consider how your own choices, from diet to landscaping, affect water use. The Colorado River's story is still being written by natural processes that have shaped this landscape for millions of years and by human decisions made every day across the watershed. By understanding both the visible crisis and the hidden dynamics beneath the surface, we can work toward solutions that respect this river's limits while sustaining the communities and ecosystems that depend on it. The choices we make now will echo through this landscape for generations to come.